Okay, so this is for ECE 3300 Lab7, and this is the BCD counter upgraded. So in this lab, we have to make an 8-digit BCD counter with the ability to upload to a specific counter module, one of the 8 digits, and it also has to have speed control with the clock so it can count faster or slower. So to go over the design, we first had to make an overhead, just like a general high view of like what we want to design. So we can see here we have 4 individual blocks, very distinct. So you have a demux, the actual 8-digit counter, the 7-segment driver, and then the clock controller right here. So this clock controller is pretty simple. It's just a counter, and based on a 5-bit input, which I forgot to put right here, would control the speed. So essentially you have a 32-bit counter, and that 5 bits will control which bit in that counter will act as the clock. So if the input is, let's say, 12 in binary, it'd be the 12th bit of the 32-bit counter. And that would slow down the 100 megahertz clock, which we have right here. And we also have an enable for the counter, so when the counter stops, our clock controller stops because that is the only thing that it's connected to. Next we have our demultiplexer. So this controls the loading. So we have a 4-bit load value because we are working with BCD, and then we have a load select, so that's a 3-bit, which would select which of these displays we'd want to go to and push that value to, I guess the counter. And then we have this load, which is like the enable for the multiplexer, and what this does is it essentially lets us load values and stopping the count, but it also acts as a way to send a load signal, since we have a select load signal and a select value signal. So the value is obviously 4, that's the 4 bits being passed through, and then in this counter we're going to need some sort of way to determine which display we're going to, while also knowing when we should load and stop counting, so that way all the displays stop counting. So we did that with a load select and a value, and then this load enable right here. So when enable is low, all of these load selects will be 0, so nothing's going to be loaded up here. Okay, so now let's go to the counter module. So this is the basic counter block that we went with, since this is the core module right here. Oh, actually, I forgot to just explain the 7-segment driver, just the ones that we've done in all the other labs with the system clock and a clock divider. Okay, so here's our counter block. We have 5 1-bit inputs. We have the load signal, the up down signal, where up is counting up when it's 1, counting down when it's 0, reset signal, enable signal, and then also a clock. And then we have this load value, which would be the 4-bit BCD value. And then we have 2 outputs. We have a BCD output and then a rollover. So what this rollover is once the BCD value goes from 9 to 0 or 0 to 9, it sends out a signal letting the next display know, like, hey, I am changing value from a 0 to a 9 or a 9 to a 0. And then we made this little feedback loop for connecting the 8 digits together. So based on our load select, we're ANDing all 8 of those bits together, and if any of these are high, or it's supposed to be an OR actually, but when any of these are high, then this will be high, so it'll let all the other ones know that like we're in load mode and we're not going to enable counting. Okay, so here's the big, I guess, model of what we're doing. We have our reset signal, up down signal, and then the enable and the not load feedback, the load feedback being the OR of all the load selects. So when one load select is enabled, then all the other ones are going to stop counting, and that would also be tied to our enable line. So all of these are common signals amongst all of these counters right here. And then up top we have our load select and then our load value, so 32-bit and an 8-bit. So they all connect to their respective displays. So load select 0, 1, 2, 3, 4, 5, 6, 7, and then our load value should be 4 bits each. So from 0 to 3, 4 to 7, 8 to 11, 15, 12 to 15, 16 to 19, 20 to 23, 24 to 27, and then 28 to 31. Okay, now we're going to start to explain the code.
So this is our code explanation for our BCD Up Down counter. First, I'm going to go over the top module, and then I'm going to go over the smaller modules that are instantiated. So first in our top module, we have all our inputs. So we have our clock, enable, reset, load, our up down select. We have our load select that connects to our multiplexer, demultiplexer. And then we have our switches to load in values, our clock select to select the speed, and then our outputs for our SSD driver. Okay, so first we have these LEDs to let us know what is activated. So we have a load LED, an enable LED, our up down, and a reset. Here are the wires that connect each module together. And here are all the modules that we used. So the way our design works is we have our input, our 4-bit input, and that'll go into the demultiplexer first. And depending on our select, it will choose which 7-seg we want to display our value on. And so that is why we have our 1 to 8 right here. And so out of the 8 outputs, it'll feed into the BCD up counter. And each up counter, well, this module right here will determine which segment we want to display. And then once it determines that, it'll feed into the SSD driver. And then right here, we also have our clock speed controller to control how fast the counter will go. And the input for that will be 0 through 4. So that'll be 5 switches. So here's our clock speed controller. This will determine our clock divider based on the input we have right here. It is 5 switches, so 5 bits. And then we have our clock divider right here. That'll take in our input and assign it to this variable. And then we have our always block right here. That'll determine the clock speed based off our input. Next, we made a basic BCD up counter that'll just determine whether to count up or down based on an input. And also if there's rollover. So if a digit is 9 and it increments to 10, it'll roll over to the next one. So first we have a reset right here. So if reset is on, it'll reset back to 0. We also have a load right here. So if load is 1, it'll just load the input into the output. And then right here, if enable is turned off and if load is turned off, then it'll just stop counting and display whatever's in the register. Otherwise, we have our up down right here. So if up down is 1, it'll start incrementing and it'll also determine if there's rollover or not. Otherwise, it'll decrement right here. So it'll just subtract 1 and it'll also determine if there's rollover or not. So right here is our module for our demultiplexer. It is a 1 input to a 8 output demultiplexer, and our select will be, it'll be 3 bits for our select. So we have an enable, our load select, our actual value that we will be loading into, and then our output enable, and then our output. So here's our case statement. This will basically tell us which segment we want to activate. And so the first right here will just be the value by itself. And if we go to number 1, it'll shift it by 4. So right here, our load value for our output, it'll be 0 through 3. And then over here, it'll be 7 through 4, and so on. We also have an output enable. This will tell us which segment we want to activate, and it'll be connected to a other module. So this is our module for our n-bit BCD up counter. So basically this module will take our smaller BCD up counter and instantiate 8 of them. So for our inputs, we have our clock, enable, reset, up, down. Now we also have our load value and our load select. And then for our output, we will have a load feedback and our 32-bit output. Here we have a wire for rollover. And right here, we have a load feedback to determine if any counter is being loaded with a value. So first we instantiate our module 0 right here, and we start it with our load values from 3 to 0. Our load select is at 0, our rollover is at 0, and also our output will be 3 to 0. And then we do the same with a generate right here to generate the rest of the modules. So after we create all 8 of our BCD counters, we have to feed it into our SSD driver. So for our SSD driver, we have our clock input, our reset, the 32-bit input from the BCD counter. And then for our outputs, it'll go to our decimal point, our AN, and our A to G. We have some internal variables right here. And then we assign DP to be turned off, our display select to be the last 3 bits of our clock counter. And then here's our AN enable to initialize the display. Here we have a clock divider right here just to make sure the display runs properly. And here's our display selector to determine which segment will be turned on. And here we use a multiplexer to feed into the proper display. So here we have our input. It's our 32-bit input. So depending on what our select is, it'll connect directly into the bits that we fed into it before. And then finally, we have our digit to 7-seg decoder. This will just make sure that the segment actually displays the correct number we want.
Hello Professor, I'm going to be explaining the test bench and the waveform for this lab where we are asked to upgrade our BCD counter from a previous lab. So here we are making the registers and wires for testing in our test bench. And here we are instantiating our module, and I included something called out value to display the value for the output of the counter. And here in this always block we are starting the 100 MHz clock. And here we are setting the initial values. So enable is set to 0, so the counter will not start counting. Reset is set to 0, so the values are not resetting. Load is set to 0, so we're not loading values. Up down is set to 1, which means we are going to be counting up. Load select is set to 0, so that means if we were to load values, it will load the far right 7-segment display. And the load value is set to 0, so if we were to load values, it will load it with a 0. And speed is set to this value, which is the fastest clock speed. And after some delay, the enable is set to 1, so that means the counter will begin counting up or down. In this case, since earlier we set up down equal to 1, it will be counting up. And then after some time, the reset is set to 1, which means the value will reset it will be set to 0. And then after some time again, the reset is changed to 0, so it stops resetting. And then we set the load value equal to 1, which enables loading values. And here the value that we want to load is set to 9, and we are loading it into the ith digit, which will start at 0 and end at 7, which means we are going to be loading 9 into all 8 of the 7-segment displays. And then here we are turning load off after some time of counting, and then we set up down equal to 0, so it'll begin counting down. And then we reset equal to 1, so it'll reset the values. Reset is set back to 0, so it'll stop resetting and it will begin counting up. And then here for this for loop, we are changing the speed of the clock. Here is the waveform for the simulation for the test bench. So here we can see the enable is set to 0, so we're not going to be counting. The value stays at 0 until enable is set to 1, which means we're going to be counting. And since up down is set to 1, that means we're going to be counting up. And then if we zoom in, we can see that it counts up from 0, 0 to 1, 2, 3, 4, 5, and so on and so on. We zoom back out, we can see that the reset is set to 1, and we can see the value is then set to 0. Here, reset is set to 0, the load is set to 1, and that means we'll be loading values. If we zoom in, we can see which digit is being loaded. So here we can see that the load select is set to 0, and that means we will load the 0 bit with the load value, which the load value is 9 here. So we're basically loading 9s into 8 of the 7 segment displays here. And once the load select is 0, we load 9 to the first bit, to the second bit, so on and so on. And zoom back out. Here the load is set to 0, so we're no longer loading values. And since the enable is 1 and the up down is 1, we're going to be counting up. So if we zoom in, we can see it counting up, starting from 9999 and rolls over to 0, and then begins counting up again to 1, 2, 3, and so on and so on. Zoom out. We can see here that the up down is set to 0, and it will start counting down. If we zoom in, we can see the values: 9999, 9998, 7, 6, 5, so on and so on. And then here, the reset set to 1. The value is then set to 0 because reset set to 1. And here, reset set to 0, and the up down is then changed from 0 to 1. So this is changed, and we're changing the speed values. So if we zoom in, we can see that the speed is changing values, and you can see here that we're counting from 0, 0, 0, 1, 0, 2, but we're counting at a slower speed since we're changing the speed values. So we're going to be counting from 0, 0, 0, but at a much slower time compared to the beginning, as you can see here. And this is because we changed the speed value, and this is it for the waveform. Thank you.
Okay, so now we're going on to the board demo. So these first 5 switches right here control the speed of the clock, and then this is an empty switch, and then we have these 3 being the load select, and then these 4 being the load value. This once again being another switch that does nothing. I'll set it in the middle just so that way it's a little easier to know that these don't do anything. This is the enable, and then this is the up down. So I'm going to start counting up, and we're going to see that it's going super duper duper fast. To reduce the speed, we're going to start putting up these switches, and we can see here with a value of around 20 or so, we can see that the count slows down to a reasonable speed where we can actually see what's going on. And we can see that it's counting up right now based on this. And if I pull this one low right here, we'll see that it starts counting down. Okay, and then now we can reset everything. We can see that it rolled over just fine. And then now I'm gonna hold the load. We can see that our load LED is high and load is high. So now based on this, I'm going to pass, I could see that we're passing zeros to all the values just based on the fact that our load value is 0. So let me pass all these in. Hold on. There we go. Okay. So now we're on the least significant. Let's make that a couple up. And then let's pass 8, we can see 8, and we can see 9. Oops, let me put that low again. Sorry. Okay, and then we could do C10, F. See, it always stays 9. Let's start passing it down. 3, 1, 2, 4, 5, 6, 7. Okay, so we saw all the values be passed through. So I'm just going to keep 6 there. And then let's pass 6 to all the displays. Is that the right one? Let's see. 5, 6. Okay, yeah. So then these ones right here. Oops. Okay, so now we see we have all 6s. And we should be counting down. And that's just what we expected. So everything's working just fine.